Here's something I find interesting in first-order logic. This sentence right here is the completeness theorem, which what it really just says is, well, kind of going down. If I have a formula A that is true in some set of for every set of statements in sentences in this set gamma, then that formula A is provable in this set. Now, the proof for that is a little bit weird and a little bit wonky and wacky because, well, I'm still trying to figure out how to do the proof for the first part, which, from what I'm told, is that you just do an induction scheme from if I'm trying to prove soundness, which in this case, if my formula A is provable in gamma, then gamma is a model for A. Or in this case, A is valid in gamma. I think I said that correctly. But what I find it interesting is that the proof for the completeness requires the idea of consistency and something that I believe Heinken, however you pronounce it, uses, in this case, what he calls the model existence lemma, which basically just says that if I have a consistent system, then that system has a model. And for what it means for something to be consistent is that you can prove anything. You can't prove any contradictions. In terms of notation, that just means that any contradiction is not provable in this set. So the proof is pretty straightforward, using the model existence lemma. So instead, we're going to use, I believe this is contrapositive and not contradiction, but I could be wrong. For those who do know the structure of the proof, please let me know in the comments. So this is how the proof goes. If A is not provable in gamma, then that means our system is not consistent, so we have to add something into it in order to make it consistent. So we'll add not A into the set, and that gives us a consistent system, which therefore, by the model existence lemma, tells us that that system right there has a model, which means that there is an element there is an element in the set, in the domain of our model, where gamma is true and not A is true, which therefore by definition, implies that A could not have been true in this set, which by contrapositive proves completeness. I think it's by contrapositive or contradiction. Please let me know. So that's something I found interesting. Bye-bye.